All right. Whoop. We got something like this. Baseball started yesterday, right? Brewers win 5-4. Now, force times distance for work. We know how to calculate forces already. We just got to put some distance in here. So, here's some of what we're going to talk about here. So we can go right to the next page. This will look familiar. If we zoom this in, focus as best I can. If this person is pulling, what we really want is force applied in the X, right? How are we going to get force applied in the X? Cosine, right? So this is nothing new. Here's the force applied. There's our angle. What is this force applied in the X? This force applied in the X we know is force applied cosine theta, right? Whatever the angle is, it's the cosine. So then if we keep track of the distance, we have this equation. Work equals, it really should, I wish they would put the D. This right here gives us force applied in the X, right? Force cosine theta is just force applied in the X. Multiply that by the distance, right? I don't like the way that looks, but... So what's our units going to be? Force is going to be in newtons, and our distance is going to be in meters. So for work, we're going to have Newton meters, which is a joule for units. So that's just work, force times distance. But we put the cosine theta in there to make sure it's force applied in the X direction. Now, we're only doing work if we're applying the force in the direction that we're trying to move the object. So here comes the conceptual question. As long as this person does not lift or lower the bag of groceries, they're moving at a distance, right? But what is, if this is my force applied up and they're moving this direction, what is this angle? 90. So if the work is done is FD cosine 90, what's the cosine of 90? The cosine of 90 is 0. No work. No worky. 0. But if they're lifting or lowering, now when you do the homework, I don't like all this positive work and negative work. If you lift up, I'm still saying up is positive. If you let it go down, gravity does work. So technically, if you lift it up and let it go back down, the total work is 0. I'm going to try to stay away from all that nitpicky kind of signy stuff. I know. You know, if you lift up the object, you're doing work. So, but realize when you do the homework, it'll say how much work is done by friction or gravity or something like that. So the solutions are out there too. And number 5 on the homework, I converted it to English or from English, so it's a little bit different. So back to our lawnmower. So we are doing the same thing we've done previously. We are just going to keep track of how far this thing moves some distance. Let's say we move it to here. And in this problem, we're moving it 25 meters. Well, obviously, whoever moves it farther is doing more work. But the solution is still the same. The solution is still the same. So it would look like this. We got to go, our lawnmower handle's going 35 degrees down like this. "35 degrees with the horizontal would look like that for our handle. The force applied along this handle is 75 newtons. So all of this should be the same. Let's square this off. Do we have friction in this one? No, does it say friction? It does not. Okay, so if this is 35, this angle here is 55. And obviously if this is 90, this angle in here is 35 degrees again, right? Now, our x component is here. This would be our x component up here too if we squared this off, no matter what. That's the force applied in the x, right? These are exactly the same. Probably looks even better to use the top one. So we know that force applied in the x is going to be equal to force applied cosine 35, right? So how much work are we doing? This is force applied, so we've got 75 newtons. We're going 25 meters. Cosine 35. Newton meters, which is same as a joule. Well, if we have a force distance, the work done should be the area under that curve. if you have a varying force that's not constant, you can end up with some goofy looking curve. Let's say we've got something that looks like this. I'll use this axis here. Distance in meters. We'll split it up into 10, 20, and we'll split this up into 5, 10. It'll look something like that. Force varies. So what's my area under this curve? What's the area of this much? How much right there? This is 100, right? 5 times 20? 100 joules there. How much here? One half the base, which is 10 to 20. 1/2 of 10. What's my height? 5. So we've got half of 50. 25 joules, right? You have something like that, 125 joules. Now, for a previous class, I've handed out something like this. Don't write this down. And I gave I said, I think I did 5, and I think I said this was 5, 10, 15, 20. Find the area under that curve. It's very simple. This is a good trick to keep up your sleeve. What you do, how much is this part right here? That's 25, right? You cut this square out, mass it on a balance. Right? Then you could have 25. You know that 25 joules is equal to 0.125 grams. There's your conversion factor. Then you cut this curve out, weigh the rest of the paper. All done. You do it by weighing paper. Huh? What's that? Yeah, you would want it. Yeah. Right? You do it by weighing paper. And you could leave the whole thing curved, and you could measure out a perfect square section here. Figure out that as your conversion factor, right? And you weigh paper. Slick. But you just got to, you actually got to take a scissors to cut that out. It works slick. Okay. I'm being totally serious. Yeah, totally serious. You weigh the paper. The paper's uniform. Yeah. Somebody gives you a crazy problem like that, try to find some kind of square piece, weigh the paper, and then cut the whole thing out. Yeah. No, cut up your... That's a good one. Cut up the test to do it. You might be out. Well, you don't have to bubble it, right? So I guess you can cut up your test. Now, kinetic energy. Now, check out this units for sure. Previously, a joule was equal to a Newton times a meter, right? What's a Newton? And F equals MA is a Newton, right? F equals MA is a Newton, and MA is kilogram times meter per second squared. And if you still multiply it by this mass, then a joule is a kilogram meter squared over second squared, which matches my kinetic energy units, right? A joule is a Newton meter, but if you break it down, you really get kilograms meter squared over second squared. Okay. If you change the speed of something, we're not going to change the mass. If we change the speed of something, we've got to do a little bit of work, which is called the work energy theorem. So we just say that our net work is equal to our change in kinetic energy. And technically, this would be kinetic energy final minus kinetic energy initial. If we do not change our mass, this would be 1/2 mv final squared minus 1/2 mv initial squared. And we can put our force times distance in here if we want. Then we could factor out, what can we factor out of this side? We can factor out 1/2 m, right? Okay, try 1 through 14 on this. The answers match except for number 5. I've converted number 5 on your answers. This stuff is in English, so you do have the answers to all these. It started with a few quiz problems in the beginning as well. Okay. Stay out of trouble this weekend.